Hello everyone, and welcome to the 55th episode of TechLifeSkills with Tanmay. My name is Tanmay Bakshi. Thank you very much everyone for joining me today. And as you know, we've talked a lot about the world of machine learning on this show. And today, I'm very glad that we can take even more of a sort of technical and mathematical deep dive into the world of machine learning technology, specifically scientific machine learning. We're being joined by Chris Rackauckas. Chris is an applied mathematics instructor at MIT. He's the director of scientific research at PUMAS-AI and the lead developer of the SciML open source machine learning organization. So as you can tell, Chris does a lot of work with scientific computing and scientific machine learning, those kinds of technologies. I'm super excited to get to talk to him about some really interesting new stuff like, JuliaSim, introducing machine learning technology into physics simulations and so much more. And so now, without any further ado, let's go ahead and welcome Chris to the show. Hi, Chris. How are you?
Hi, I'm pretty good. How you doing today?
Doing very well. Thank you for agreeing to be on the show. I'm super excited to see what you'd like to share with us today. But before we get into that, though, I do want to say really quickly, would you maybe like to introduce yourself? Tell everyone a little bit more about who you are and what you do?
Yeah, you gave a pretty good introduction, but yeah, I'm Chris Rackauckas. I'm a applied math instructor at MIT. I am the director of scientific research at PUMAS-AI. I am the lead developer of the SciML organization, which has these packages like differential equations.jl that a lot of people make use of,
Mm-hmm.
and also a very recent title. I'm now also the director of modeling and simulation at Julia Computing. That one came in a little too late for you to have that knowledge, but this is all related to the new JuliaSim product that recently was announced. Yeah.
Well, congratulations on that. That must be exciting. Probably people joining on the live stream might know this. A little while ago, I had Viral Shah and Kino Fisher on the show, CEO and CTO of Julia Computing, everybody. So feel free to go ahead and check out their episode as well. I will link to it in the description. It was really fun. We talked a lot about Julia, why it's so special, and how that ties into the world of scientific computing. As a matter of fact, if you don't mind me asking, this is something that we get. It's a question on pretty much every sort of show where I bring on a developer, someone who codes. So I thought we'd start off with a pretty fun question. And I know that even though this is a fun question, it's a bit more loaded than a lot of people imagine. It's something where it's a lot more complex than it seems on the surface. But what is your favorite go-to programming language? If I were to just give you a task right now, what would you code it in?
Oh, 100% Julia. No questions asked.
Wonderful. That is amazing. And as a matter of fact, everybody, again, Julia, one of my favorite programming languages as well. And of course, I've written a book on it. So feel free to take a look at Tanmay Teaches Julia to learn about the world of Julia. Towards the end, I do introduce you to the world of machine learning through Julia. And that's why we're here today to talk about scientific machine learning technology, since I know that's what you're really passionate about. So before we begin, how about we take a little bit of a let's just get our toes wet here. So could you maybe tell us a little bit more about what scientific machine learning technology actually is?
Yeah, so scientific machine learning is mixing scientific computing with machine learning, right? Scientific computing is actually a quite technical term. It doesn't just mean computing with a science involved. Scientific computing really means something around modeling and simulation of physical or chemical or biological systems. So when you think about physics, right, it basically gives you a simulation, right? You have these equations of gravity, and then you say that if I have these gravitational bodies here, I have this thing moving around, and then you can calculate out where everything should be in the future, right? Machine learning is this, so that's what's known as mechanistic modeling, right? So we know the mechanism. We understand like, oh, gravity is the thing that does something, and if we look at what happens, in this system due to gravity, or if we have what happens in this system due to electromagnetic effects plus friction,
Mm-hmm.
right? If you pick the mechanisms and you model it, you can predict the future essentially. Machine learning is doing something very different, right? It's non-mechanistic modeling. It is, if I have given sets of data, can I learn to do a prediction, which is f of x equals y, right? You usually think about machine learning as, something to do with data science or whatnot. Throw that all away today. At least, that what it's truly doing at its mathematical level is just there's an input X, there's an output Y. You see a lot of input output pairs. Learn the function f of X that brings you from X to Y, right? A neural network is just a good object for doing that, along with SVMs and all these other types of methods. And now the real question comes, people have been putting these in two silos for a long time, right? And in one sense, you have mechanism, and you're like, I know the physics that predict the future. In another hand, I have a bunch of data, so let me put some data in to train a neural network, and that predicts what's going on. And so there's two silos, but can you bring those two silos together? Does it make sense to bring those two silos together? And that is scientific machine learning, right?
Mhm.
So the real high level idea and the driver behind a lot of this is, if you're to try to train a neural network to predict, let's say you're throwing the ball, right? And you throw a ball, you have a bunch of videos of this, and you keep on throwing a bunch of balls, and you're trying to make the machine learning mechanism train to learn where the ball will be in the future, just if just from the way the pitcher's hand moves and a little bit of the trajectory, right?
Mhm.
If you're trying to do that with a neural network, it's going to have to learn a whole lot of things, right? Like it's learning how to find the ball, and it's learning how to it's learning how to find the ball in the image, and it's learning how the ball usually moves in the image to then be able to predict. It basically needs to learn all the laws of gravity, some things
Mhm.
about friction, etc. But in the physical way is, you'd have someone sit there tracking it and find the actual coordinates of the ball, and then you'd be like, oh, if this is the ball and this is approximately how much wind friction I have, here's the gravity, you predict it, right?
Mhm.
Scientific machine learning is in the middle, where you say, I'm going to have a machine learning framework take images from the ball and turn it into things that then go into my physical simulator, and then I'm going to train the physical simulator to learn something about friction, which maybe I don't know about, and I'm going to learn the friction simultaneously to learning how to do the image processing.
Mhm.
And so you're mixing physical models and machine learning in a very seamless way. Um, Big introduction, but I guess hopefully you're in the right mind now of, like, this really is something where there's scientific models, there's physics and chemistry, all that information is in part of what we're doing in this predictive in this predictive style.
Right, that makes a lot of sense. And a little while ago, actually, this reminded me of an application I was trying to build, but didn't end up actually, completing. It was a little application where you could set up your phone on like a tripod, and I love table tennis, so you'd be able to use the new lidar sensor on the iPhones to detect where the ball is, how far away it is from the camera and stuff, and track the ball as you play table tennis, to then do things like prediction of, right as someone hits it, can we tell where it's going to land before it actually lands there and stuff like that. And actually, it would be interesting to see if we could actually end up doing something similar with what I learned from you today, and using the resources that you recommend. So we'll definitely take a look into that. But speaking of these sorts of combinations of models, and where they can be applied, what are some of the use cases for scientific machine learning models? Like, what can you do with these sorts of things?
Yeah, so a lot of use cases for scientific machine learning are where you do not have enough data, or where you
Mhm.
have physical things that need to be conserved, right? In table tennis, if you're a little bit off in your prediction,
Mhm.
you might be okay. But what will happen is the machine learning framework is always going to violate a few things that we know it shouldn't violate.
Mhm.
Conservation of energy, right? So if you can somehow get how much energy you had a moment from the hit, use some information from the sound or whatnot to be able to predict the energy, then you can really constrain where the ball must be able to go, because there's only so many places that are actually energy conservative, right? And we know energy has to be conserved, right? One of the main ways that scientific machine learning is finding a use case already is in environments where it's very difficult to get a lot of data, or where it's very expensive, right? So I work as my part of what I do is in PUMAS-AI, which is in pharmaceutical modeling and simulation.
Mhm.
Some of the key hits that we had is, PUMAS is used by all sorts of companies around the world, such as Moderna, which has been last year that wasn't as big of a deal, but then after what's happened in 2020, it's been a pretty big deal, right? And One of the nice things about scientific machine learning in the context of clinical trials is that you know that you won't have enough data to train a neural network, right?
Mm-hmm.
There's a lot of things that people are doing with retroactive studies, where they're saying like, oh, if I had, 1,000 images of patients who died, then I can, diagnose whether they have cancer. And it's like, that's not a very satisfying clinical trial method, right? You can't have the first set of your clinical trial be your training data for a neural network. Like
Yeah.
it's never going to fly, right? So you already have to have some kind of predictive model going in, but then what you want to say is start from this predictive model, use that to be able to find out who we're dosing and whatnot, but then have a machine learning mechanism automatically start making that model better, right? So we start with some first intuition. We start with some principles where we say, this is how we think the chemicals work in your body. It goes into one department, and then it attacks with this other chemical. This catalyst comes in, right? So you can model the whole chemical reaction system. You say, this is pretty close. And so on a person with a weight of 180, you should get this dose versus a weight of, 20 pounds. Well, I guess, so dogs should get a very different dose than a human. Can we just make a prediction and be able to change between them and, a small child versus, man versus woman, all these different differences. You can then try to predict from this chemical model. Of course, that chemical model is incorrect because your body has hundreds of thousands of proteins and in chemicals involved, and we're only modeling 30 of them. So, we're going to be off, but it's surprising how close you can get with just a crude model, right? And so,
Mm-hmm.
where scientific machine learning comes into play is you could say we can start with this model. It gets us 90% of the way there. Machine learning then brings us the rest of the way there, right? And this makes it so that way you need a lot less data because now machine learning is just learning, it's learning that little piece, it's learning the residual. It's not having to learn everything about the system. And so you just make it easier on it. Another thing, another place where it really comes into play is in accelerating physical simulations, right? So, in physical simulations themselves, they're expensive, right? So you probably have heard something about how these large gravitation, these large simulations of gravitational fields for galaxies can take weeks, or you have these climate models that take maybe a month to do a very high fidelity run. Um, Machine learning, what it does is it approximates functions, right? And it does so pretty fast once you've trained it.
Mm-hmm.
And so if you can train a neural network to capture certain sub properties of your system, like, oh, here's how the ocean works around the equator, then you can be like, oh, let's cut out the ocean around the equator part of the simulation, just replace it with a neural network that's just spitting out what it thinks the answer is. And if it's close enough, then it should be good. And
Mm-hmm.
that's where some of the scientific machine learning comes into play again, because you're like, well, it needs to be close enough, and by close enough, well, even if it has some air, it should at least conserve energy. Otherwise, we're going to get more and more water, and the simulation will explode. And so so it does have this other purpose of really helping simulators.
Mm-hmm. And I mean, I feel like this ties into actually a few different machine learning concepts, apart from the whole scientific machine learning end of things that we've already actually talked about on the show quite a bit. Maybe an interesting analogy for people that I think they'd be familiar with would be, for example, BERT is something that I've had a couple tutorials on, the sort of whole natural language understanding engine by Google. And going to your point about just being able to learn the residual, right, learn what's remaining in this sort of larger model where humans have already said, here's a bunch of rules and our sort of base intuition. Similarly, I mean, imagine if every time you wanted to do something simple like recognizing sentiment, you had to train an entire neural network to understand natural language from scratch. That's inefficient, right?
Yeah,
When
yeah,
when you
exactly.
can start off with BERT, you have already this great neural network that understands natural language, embeds it into really nice semantic spaces, and can now just slightly fine tune to work on sentiment. And similarly, this is sort of the power that we get with machine learning models. And also, as you mentioned, being able to, replace a certain part of a system with a piece that sort of just approximates what should have been there with an actual calculation just faster. I think my favorite example of that, and this is something that one of my friends is super passionate about since he's really into gaming, is NVIDIA's DLSS. right? Deep learning supersampling, right? If you can take, for example, an NVIDIA RTX 3090 and you can game in 8K with the frame rate that you would get at 4K just because you're using neural networks to upsample from 4 to 8 or even from 1080p to 4K, right? That is incredible because now you're getting effectively what you would have gotten with 4K, but you don't
Yeah.
necessarily need to render 4K,
Yeah,
right? So,
and it's close, right? And like
yeah.
now the thing that's important in the scientific model, though, right? Like it's not just the visual, though, right? Like
Mhm.
that's where like standard neural networks can do the DLSS fine because if it's a little bit off to your eye, if it adds a pixel with more water and then less water, you're okay, right?
Yeah.
But in the scientific model, if you have that bias where it's just always adding a little bit more heat every single step, you're going to start saying that the Earth is going to heat up by 200 degrees in the next few years, and you're like, okay, there's something went wrong here. Yeah, so I think that I think that these ideas are kind of found throughout machine learning, but where it really comes into play with scientific machine learning is that there's just so many things that you have to be true in order for physics to be true, and if you
Mhm.
get them a little bit wrong, maybe you don't see something at first, but it just builds up. If you let a planet in a planetary simulation just get a little bit more energy every single time, it's just going to spiral out until it leaves the galaxy, right? Like,
Yeah.
that's where these techniques start to come into play, where you're like, well, we want to do this on physical simulations, right? People looked at this and they're like, oh, we want to put an LSTM on, to be able to train, to be able to be a new way to predict chemical reactions faster, right? And actually, one of our works looked at that, and we saw that there are certain properties of the system that make it so that way the standard machine learning methods will fail, and that's when you got to start saying, like, what are these architectures missing, and how do we make the physics be baked a little bit into the architecture so that way they can work better in these kinds of situations. Um,
Right.
yeah,
Mhm. Go
one,
ahead.
one yeah one kind of way to for people who are kind of in the machine learning kind of view. And one way that you can kind of understand this is if you're familiar with convolutional neural networks, right? That's essentially baking in knowledge about spatial locality into a standard neural network, right? It's basically saying that, a convolution is where you kind of, instead of just taking one point, you take a box of pixels where, the box has the pixels that are nearby. That is an assumption right there that the pixels nearby actually matter more than a pixel further away, right?
Mhm.
You're telling you're telling the neural network to not use the full square, which is what it would do by default, right? You're telling it to use little subsquares as the way that it's doing its predictions. And so that's like saying, oh, nearby pixels in an image matters, so therefore it should do better. And then we all know that convolutional neural networks do better in image
Mhm.
processing. And so that's like a nice use case to show that, if you have a little bit of information, you can start to bake it into what you're doing and do a lot better.
Right. So when you do have information about the task at hand, you can make those sorts of use case specific optimizations that you couldn't have made with just a sort of generalized, machine learning model. And you're absolutely right. Like within like scientific machine learning, that sort of extra element becomes that sort of robustness that we get when we have human written rules to sort of, I guess, for lack of a better word, supervise, the kinds of predictions or the output from the machine learning model itself. Now, I do see a question from the YouTube live stream. This is from Tina, and I do want to get a little bit deeper into the world of software. But just before that, I do want to answer a question since I know this is something we want to talk about. This is coming from Tina on the YouTube live stream, asking, "Hi, Chris and Tanmay. How can you get into scientific machine learning technology?" And I'm going to add to that, is the background for getting into scientific machine learning the same as machine learning? Do you need different courses? How can you do that?
Yeah, so I would say that from the students I've had, the ones that have been more successful have actually not come from the standard machine learning background. They've come from a scientific computing and physics background,
Hmm.
right? And I think that the thing here is that machine learning is becoming more and more kind of developed, right? There's all these summer schools where it's like you can go for 1 month and learn this amount of machine learning, and it turns out that that those can get you up and running in machine learning quite fast. Whereas you really need to know the physics deeply in order to be able to do scientific machine learning, right? Because
Hmm.
you're really like I mentioned things like, we have, conservation of energy, and so you're going to require that. And so, if you've had at least, enough physics up to Hamiltonians, you should be good to handle some of these methods. But you can see that how that's going to go. There's all these things like gauge invariance and everything. If you want to understand like how to put gauge invariance into a neural network, learning the basics of a neural network isn't too bad, but learning all the things that you need to know for every subfield of physics, you really do have to specialize in some field of science, and then pull in machine learning into that, kind of rather than the other way around, just because each scientific discipline has its own full language and everything. I mean, you still definitely want to do some machine learning, and so at least at MIT, normally the students will take like the two major machine learning classes plus the scientific background. But usually that's what we find out works better, rather than someone who's doing a PhD in machine learning and then takes one physics course taking one physics grad course as the only physics course you ever do is gonna be a little wild. So
Yeah, again, the purpose of the domain is to be able to incorporate machine learning into this world of physics, and so it makes sense
yeah.
that you want to specialize in physics to actually be able to do that. So machine learning is the tool you're using in the field. It's not the field that you're using the tool in. So I think
Mhm.
that's important to keep in mind. But now, though, I do want to get a little bit deeper into the world of software, and I do know that within machine learning specifically, software is a big thing, and that's something I've also been incredibly passionate about, which is why I love languages like Julia and previously frameworks like Swift for TensorFlow, although we've seen that didn't exactly play out all that well, things like that. Because when you empower engineers with better software, you then enable them to build better tools. And I wanted to know, in the world of scientific machine learning, how does that play into the world of software as well?
Yeah. So the interesting thing about software for machine learning, right, is that it really comes down to automatic differentiation. There's this idea of being able to call gradient on a piece of code, and you get the gradient, right? I mean, if that was 100% easy, you wouldn't necessarily have a machine learning framework, right? The difference between machine learning framework and code in the language would be essentially zero if you can just kind of say, here are my matrix multiplications, stick them on a GPU, and now take a gradient of this calculation, right?
Mhm,
Like that's the reason why a machine learning framework exists. So
mhm,
TensorFlow, PyTorch, they exist so that way they can stick your calculation on a GPU, and you can calculate gradients with backpropagation, which is reverse mode automatic differentiation,
mhm,
right? um, Now the difficulty that comes up with scientific machine learning is you want to do backpropagation over everything that is your predictive model, right? Because you want to basically say this whole code is something that does X comes in, Y comes out, and I want to learn neural networks in this code. And now what happens if this neural network is baked within a simulator? Let's say you have a neural network inside of a climate model. um, what what Python would require you to do is to say, well, okay, I hope that that climate model is written in PyTorch, because if you're going to use PyTorch, dot gradient, what it does, I mean, it's actually a code analysis tool, right? It looks at all this code and goes, I know this code, I know this code, I know this code. Change this piece into this derivative, change this piece, and it iteratively is changing your code around. But it can't do that if it sees something that's not within its framework,
mhm,
and so. And so one of the interesting things that happen then is that in scientific machine learning, you kind of lose, you lose your whole ecosystem. You kind of think like, oh, Python has a package for everything, and you go, okay, well, how many of those climate models were completely built within PyTorch? Okay, zero. So if we want to do, if we want to put neural networks inside of a climate model, we have to build a new one, which is like a 5 to 10 year project, right?
mhm,
So what's really interesting in this space then is not the machine learning framework themselves. What really is interesting is how flexible can we make differentiation, right? And this is so we had some work that was called generalized physics informed learning with language wide differentiable programming, where we really went through and showed that you don't have to actually even have such an idea as the machine learning framework if you make your derivative rule system be directly on the standard library of the full language, and then just treat the language itself as the underlying method, right? So
mhm,
this is actually something that that then Google pulled, for the Swift for TensorFlow project.
Mm-hmm.
Swift for TensorFlow came and it went, but Julia is still here, so
Yeah.
we won. But
Right.
you know, but really what's going on is that in Julia you can have any piece of code be differentiable, and you can also overload it by saying, hey, there's this library called chainrules.jl where you can say, for this piece of function, don't try to differentiate through it, instead use this derivative rule.
Mm-hmm.
Here's a derivative rule for forward mode and reverse mode AD. And so so basically what people have done is they tied together the whole language so that way things just generally have derivative rules. And so if you just take a derivative of a program written in Julia, then you can differentiate it. And what this means is that, if you have a machine learning framework in Julia, you differentiate it. That's how the machine learning framework works. If you actually go look at the code for Flux, it's like TensorFlow, but if you chopped off 99% of it, because 99% of TensorFlow is how do you take derivatives and how do you JIT compile the code and how do you put things on GPUs,
Mm-hmm.
right? Very little of it's actually for machine learning because these are the three real difficult software pieces, and that's just handled at the Julia language just does that.
Mm-hmm.
And so for machine learning, then you're like, okay, so you get something like TensorFlow, but so what's the difference? Like, why should we care, right? But the real difference really comes into play when you have scientific machine learning, right? Because now, for example, the CLIMA climate model group, they've been building a climate model for what, 3, 4, almost 5 years now, with the large set of money, with this large team, and it's in Julia, which means that we can differentiate it. So when I talk about things like, oh, how do we, where are we trying to test, scientific machine learning in a real climate model? We don't have to rewrite a climate model because we have a differentiable program, a differentiable climate model there, because differentiation works on the whole Julia language and this code is in the language. So we have cases like quantum circuit simulations, right? So people are trying to figure out how to build the smallest quantum circuit to solve certain problems, and you can just use machine learning on quantum circuit simulators because quantum circuit simulators that are written in Julia are, they're differentiable. So physics simulators are just, well, the differential equation library is written in Julia, so anything with a differential equation, which means anything that's physics, biology, or chemistry, you
Mm-hmm.
can throw it in the differentiation, and now you can start to say, well, I can just stick neural networks in anything and start to be, what's the neural network version of this or that or this or that. There really is no machine learning framework at that point, and that's what really gives us the freedom in Julia. So, kind of really pulling it all back together. The real software aspect here is that you want differentiation to work at a low enough level that it works for the whole language. And Julia has been able to really shine in this space just because of how it's built its differentiable programming. There are kind of small tools here and there in PyTorch, like there's like this Torch Diffie-Q, but you'll see exactly where its limitations are. So, for
Mm-hmm.
example, it doesn't. The only stiff integrator that it has is the one from SciPy, but it doesn't have. It doesn't allow GPUs or anything because it's kind of calling into the SciPy one. And why is that? Well, it's because SciPy is using a Fortran code, and so now it's trying to make a Fortran code work inside of PyTorch. They can hack it a little bit, but it doesn't have full compatibility. And
Yeah.
once you start getting to this thing where you're like, I want to do something very non-standard. I want to stick this machine this scientific computing thing into machine learning, and I want two people who built packages who never worked together to have their packages work together. You need a form of composability, and that's really that's really where the Julia language has been shining in this field.
Wow. I mean, it's like, Julia, you just managed to make me more passionate about the language every time I hear about new stuff about it, right? And it's really incredible to think that this sort of differentiation is built, I mean, as you mentioned, directly into the language and down into the actual compiler stack to the point where, again, as you said, you could have two completely different libraries, and it's not like there's just one machine learning framework that everything needs to be written in. Instead, the fact that they're written in Julia means that you can just differentiate through them because that's just standard. It's differentiable by default. That is incredible.
Yeah. And I think that there's a really interesting point in there that the reason why it exists is actually kind of a crazy happenstance, right? It's like we want to go back and say Jeff Bezos, God of all gods, realize that 10 years down the line he's going to want language-wide differentiable programming, and so he designed a type system that made it easy to do, right? Like we want to believe it, but that's not actually true. What ended up actually happening with Julia is that we wanted to say, well, let's build a dynamic programming language which has the simplest syntax possible, that is then able to infer what all your types will be and be able to use multiple dispatch to choose the fastest code path for that to work. It turns out that those exact primitives for how Julia was built is exactly the same primitives that you need to do what's known as abstract interpretation, which is to take a look at someone's code and say, I'm going to run it differently. Right, because what you need to be able to do is you have to be able to say, let's push forward a little bit of information, and then from that information, let's choose what way we're going to compile and build this function. Now let's go one step forward and do this again, right? So, that's how type inference works, right? So, because it runs your code forward using an abstract interpretation where it says, I'm going to run your function where I'm just computing what the types will be out of each function, but I'm not going to actually do the computation yet, though, right? So it has this whole system in there, and turns out the automatic differentiation libraries use exactly that same mechanism, right? Because they're basically just like, I'm going to run your code, but instead of running your code, at each step, I'm going to replace it with this derivative rule, which comes from chain rules jail. The way that it's doing that is exactly the same as this type inference kind of compiler pass that Julia is doing. It also means that there's so I actually wrote a real recent blog post which has showed that differentiation is not the only mathematical problem you can solve like that. You can do things like find the sparsity pattern of a Jacobian, right? So a Jacobian matrix is the matrix of derivatives. Like if you have n outputs on n inputs, what's the derivative of nth output with respect to the mth input? It turns out that you can say, well, instead of doing computing, let me just track in a program whether two things ever combine. Do I ever multiply this variable and this variable? If you take someone's code and you just start pushing forward, like, oh, which things combined at this step, which things combine at this step, all things that combine is all the non-zeros in all those derivatives. Right. And so, it turns so it's this crazy happenstance that, the one thing that you needed to make Julia a fast programming language is exactly the same analysis that you need to make differentiation language wide. It's the same one that you need to do automatic detection of sparsity patterns. For all these crazy things now, you can actually do uncertainty quantification in someone's code automatically with this. It's all this kind of same idea of abstract interpretation, which is really fun. Kind of a long rant there, but it's if you haven't dug into that topic, I have a real recent blog post that shows that if you just allow yourself to do step-by-step code rewriting, there's so much you can do.
Wow. I mean, yeah, no, first of all, that wasn't a long rant. That was a fun one. I mean, my friends know sometimes I'll go on weird long rants about things, but they're always about fun stuff. And what you just covered is so fascinating. Things really do have a way of figuring themselves out. And it's an interesting sort of correlation there, where, as you mentioned, the same thing that was needed to make Julia a fast language and sort of as expressive as it is today, it was the same thing you needed to actually make it that applicable for scientific computing or scientific machine learning, these sorts of things. And I do want to dig deeper into that, but actually before we do, I want to take up two quick questions. One from actually Tina, but I think we just covered that quite a bit, and in fact, if there's anything else you want to add, I'd love to hear it. Asking, why is Julia your favorite programming language? So I think we just covered it quite a bit, but again, anything else to add?
I do want to add something there, right? I was
Definitely.
I was touching on this point of composability, right? Which is that you can define how your code works by how it transforms other code in a way that is at the compiler level, so that way it's 100% efficient, right? Now, we've gone overboard with that in the SciML ecosystem because, I mean, we want to just kind of throw together people's codes willy-nilly. And so one of the things that's true about the differential equation solver is that it writes the mathematical algorithms at a abstract level, right? So it says, the Runge-Kutta method for solving a differential equation is this general thing. If you're actually to ask, like, oh, what are the registers that it puts the floating point numbers in? It goes, floating point numbers, we haven't even talked about that yet, right? So it's written at a completely abstract level. And when you actually give it, you're like, I'm trying to solve this equation, and my initial condition is this array of floating point numbers. That's when it goes, let me build a code for floating point numbers, right? And then then it goes, okay, here is a code that is perfectly efficient on your floating point numbers, and you can actually see that it will outperform C++ and Fortran libraries because it's able to actually do more optimizations because it's delaying that process until it knows everything about your chip and all that kind of details, right? So you get some really nice performance stuff off of JIT compilation. But it turns out that this idea of keeping an algorithm abstract is really powerful because then you're like, well, does it support running on does that differential equation library support running on a GPU? I never wrote it to, but it does anyways because if you just say my initial condition to my equations is this GPU array of floating point numbers, it goes, hold on one second, let me compile something, and oh, here we go. Here's your code for GPU. Because all it keeps is this technical, very abstract form, and it builds a new one for every single input it sees. And so GPU arrays, no problem. And so there was actually one real crazy instance of this where there was someone who opened an issue on one of our repositories because they were solving boundary value problems, which, so boundary value problems are, a little bit more obscure than ODEs. They're solving boundary value problems on GPUs with quaternion numbers. I don't know if you know quaternion numbers, but they're like complex numbers, except if you had four of them, and they have this weird rule so that way they don't, so it's like the weirdest thing ever. But some people look at it because it's a good way to be able to do 3D rotations without getting something called gimbal lock. If you only allow yourself to have 3D vectors, there's a way to rotate where you can get a singularity, right? So sometimes you want to use a quaternion number, right? It's really obscure thing, right? So throwing that with a boundary value problem with the GPU, like very few people solve BVPs. Even less people use quaternions. Even less people are throwing that on a GPU. Even less people are putting all three of them together, right? There's probably only one person in the world who ever wanted this. The differential equation solver said, oh, you wanted to do this boundary value problem on a GPU arrays of quaternions? Let's generate the code. They opened an issue because they forgot to, the error that they actually had was that they defined 5 out of 6 boundary conditions that they needed. So so it had nothing to do with the code gen process. We just were like, oh, here you're missing a boundary condition, and they put it in there, and they're like, great, you have the best GPU based quaternion boundary value problem solver out there. The only one I could find, and I'm like, yeah, it's because I didn't even know it could do that.
That is incredible. I remember back when I was I think 11 or something, when I was getting into like the Swift programming language, because that was like one of the I had started learning it the day it was released basically. I was really fascinated by its generics, and that was my favorite thing about Swift, because back then I didn't really use all that many advanced programming languages. And then when I got into Julia, that was just to a whole other level, as you mentioned, in terms of like the composability of code and how things can just work together with the JIT compiler. It's incredible. It really is.
The real nice thing with multiple dispatch is it's not opt-in, right? Like, a lot of people are like, oh, I'm going to opt into allowing this feature in my library.
Yes.
No, what you want to do is you want to let anyone just do anything to your library. So another really fun one is measurements.jl. It's numbers with error bars, right? And like in a high school physics class, you might have done something like where you're like, oh, if I have x plus or minus y and I have v plus or minus w, what happens when you add them? What happens when you multiply them? What happens to your error bars, right? You can turn that into arithmetic. And so then once you've turned that into an arithmetic, you have a number type that is then dispatching all of your pluses, multiplies, sine, cosine, all of those on how you should be propagating, your error bars. And so it turns out if you stick that into a differential equation solver, you solve it and you get error bars at the end of your simulation. If you stick that into a neural network, you get that and you get the output in the neural network with error bars. And it's like, I bet I know the way that I found out about this is that someone posted on the Julia discourse telling me, hey, it's really cool that your library has this feature. And I was like, thank you for letting me know. So composability is like a very strong thing.
Wow, that is absolutely incredible. I mean, as you know, programmers just like, wow, you can do that. You know, it's pretty incredible. All right, now one more question I do want to answer, or I want to ask you from Shubham. This one's a little bit further removed from scientific machine learning, but it's still related to machine learning, and I wanted to see if you have any thoughts on this. Shubham's asking, I'm currently working on deep learning applications, specifically in natural language processing. What are some good resources for studying this deep learning and NLP technology? So, are you aware of any good resources that Shubham can use?
I mean, so I'm going to give the I'm going to give the perspective of an MIT researcher here that the right way to find your resources isn't to go to a book, right? I mean, there are things in books that will do fine, but
Mhm.
really what you want to do is you want to say, I'm going to do this, right? Like I'm going to make an NLP framework that does that translates English to German. Why? Well, maybe you just want it, right? So it doesn't really matter which project you choose, but just start trying to do it. Just start trying to code it, and just ask people when you have questions. Your questions will be specific. They'll be to the point. You'll get the right exact reference. And someone will be like, oh, so and so wrote a very nice thing on how to do this in Julia with this package. Here's a snippet of code. And just kind of soak it in. Just start doing things. If you're doing things, you'll be asking the right questions, and you'll naturally learn it. One of the things that as someone who's actually an instructor at MIT, I can say one of the things that I really see as an issue in a lot of undergraduate students and also in graduate students. So even people who are PhD students at MIT. One of the biggest issues that I see from them is everyone likes to be like, I'm going to read until I know it, then I'm going to do something. And it turns out that the reason why you're at MIT or at pretty much any college is because you like reading. And so what you're actually doing when you're reading most of the time is you're procrastinating, learning lots of really cool stuff, but not at the level of being able to retain it to actually do it.
Mhm.
And so that's why I kind of say flip the script around. Just try to do it. And when you run into problems, get on the chat rooms, get on the discourse, get on the Stack Overflow, and just keep on asking the one little question that you need to get it done, get it done, get it done, and you'll learn it so much better. You'll be able to write the book by the end if you've actually written all the software to do it, from scratch. So just do it. Just try to do it.
I couldn't agree more. I absolutely love that point. I mean, it sort of goes back to the joke of, why would a developer read the documentation when they can spend a couple of hours just messing around with the library and figuring it out? But it actually does help a lot. Gaining the experience actually working on something is so much more effective than
Oh yeah.
just reading about it. Absolutely. All right, there is another question here. This one's about Julia again that I do want to get to. It's from Pro Game Fixers on YouTube, asking, what is the future of Julia and how do you see Julia in the next 10 years?
Well, I'll tell you that the future of at least the SciML organization in
Hmm.
Julia is that we're going to need to start finding some funding to be able to have all of our servers actually work because we keep getting exponential growth in the number of users. So, and that we're seeing that around Julia as well. So, we've been pumping up the amount of compute resources in GPU-CI and everything. So that way, everyone who's building GPU packages has GPUs available to them as developers and such. And we keep on having to up everything because it's just growing at this pace that's hard to keep up with. you know, Another way to say it is at JuliaCon 2 years ago or 3 years ago. I mean, I'm very deep in the community, so I go to JuliaCon and I would already know 80% of the people, right? Um, in these newer, JuliaCon last year, I probably knew about 20% of the people. And this is with me being someone who's been there, not from the start, but, very, very long time. And so, so that's telling you that more people have come into Julia in the last year than they have, in the last, 9 or so. Like this is the pace of exponential growth that we're seeing. Where will Julia be in 10 years? I mean, it's hard to kind of, I don't even know where I will be in 10 years. I might still be in this blank, dark void. I might be out in the real world. We'll never know. But at least Julia will be around for 10 years. I mean, it's hit this level that there's so many different projects in there, like these climate models, a lot of these physical simulations. The whole SciML organization, Flux. There's multiple companies doing Julia now. So you have everyone knows about Julia computing, but then you can look at all these case studies of I think this like with Julia computing we consult with like already 40 and 50 companies, and those are the ones that we know about, right? There's definitely a lot of other very large companies that are doing this and just not necessarily
Mm-hmm.
consulting directly with the compiler authors, right? So there's just so much backing in Julia right now that it's at least not going to go away, because someone's going to have to keep the code alive. And so that means you're kind of free to just be like, well, it's going to be here forever. Let's just have fun now. So will everyone was going to ask, like, do I think it's going to overtake Python or whatnot? I think that doesn't really even matter, right?
Mm-hmm.
As long as there's a strong community, then it's a useful language where there are so many companies hiring that anyone who's looking for a job, like will find one. In fact, if anyone wants a job and they know modeling and simulation and some scientific machine learning, please reach out to me. uh, I mean, like, it's just there's such a hiring spree and everything right now that it's just a good place to be working.
Mm-hmm. Absolutely, and remember, it's all about right tool for the job. In some cases, it might be that Python's the right tool for the job. In some cases, Julia, and so it's not really a matter of is Julia going to overtake Python. It's a matter of does Julia have that sort of active, growing community of people using the language or leveraging it in the right way, and it does, of course. And speaking of where you'll be in the next 10 years, whether that's the void that reminded me of one of my friends. I don't like coding in Java, so whenever I do, he says that my soul's entering the public static void. But anyway, another question from Vivek. This is from YouTube, asking. This one's again a little bit further removed from scientific machine learning, but it leads into something that I want to talk about. He's asking: is reinforcement learning a different field, or is it a part of artificial intelligence? This sort of ties into the whole question of, what is AI, what is, and all the different things. There is another episode that we've done actually dedicated to this, which I will also link to in the description. But really quickly, Chris, any thoughts on that?
Yeah, so so machine learning in general is about learning functions f of x equals y, right?
Mm-hmm.
Reinforcement learning is one of the techniques for doing this, where you have noisy measurements, and you want to say learn a probabilistic relationship or something, right? There's many different formulations of reinforcement learning, so in some cases it's hard to narrow it down to just like one thing that it does, but in general it is just another type of these methods for finding that function, right? And when you talk about deep reinforcement learning, deep reinforcement learning is using reinforcement learning to find f, where f is a neural network or a deep neural network, right? So there are some really strong connections between them. You can essentially, if I want to be something a little bit technical here, right? When people talk about reinforcement learning, what they really mean is stochastic stochastic optimization, this kind of stochastic global optimization, which is almost usually derivative free, right?
Mm-hmm.
So let me kind of break that down, because it's like kind of technical, right? So global optimization is where you say, I want to find the global, the global optima. Where gradient descent always walks to one optima by using the derivative information. You can try to find the global optima just by walking around the space, right? So you can do this randomly. You can do this with heuristics or evolutionary heuristics, where you say, let's take 10 points and take the one that had the best value, and then near the one with the best value, take 10 new points in a square around it, right? So there's all these different ways of doing it. These methods like Q-learning are essentially doing that, but what they're doing that's a little bit more than just your standard deterministic global optimization methods is they're taking into account the fact that you're getting stochastic or slightly random inputs. So if you look at what they're doing mathematically, it is this stochastic derivative free optimization. But the reason why that is what machine learning or what recurrent sorry. The reason why that is what reinforcement learning truly is because normally you're doing it like, let's say you're training a game agent, then you have one agent, you have your other agent, and you're training them simultaneously. What you're kind of getting as your inputs to one agent is kind of random because it's dependent on what your other agent is
Hmm.
doing, and so it turns out that that interplay puts you in this mathematical space of wanting to solve that precise kind of problem. But at the end of the day, it's still hitting the same thing where you're saying, I define doing well at the game as Y. What input X do I need to do to hit Y? And what is this relationship between X and Y? Well, let's learn the function F that brings us from X to Y, and then let's choose the optimal strategy in that space, right?
Hmm.
And so it's still in this machine learning space. It's just like you can almost think about it as like an alternative to gradient descent or based kind of optimization. Yeah, yeah.
I like that explanation a lot, and reinforcement learning. I think from a beginner perspective, as people are learning it, a lot of the sort of classic examples are, let's train a game playing bot or things like this. That's sort of like the classic reinforcement learning where you'd apply it. Quick question for you: have you seen reinforcement learning being applied a lot to scientific machine learning? Is that something that you do? Are there reasons for it or not to do it?
Yeah, I mean, I mean, because it is on anything, you could throw it on anything that has a simulation, right? I
Hmm.
mean, essentially, AIs have this simulation that they're learning how to control in a certain way. So you could always do reinforcement learning, but the difficulties around that is, as I said, it's a derivative-free kind of method,
Hmm.
and so it's losing a lot of really reliable information on
Hmm.
how your cost function works. So yeah, like it's not moving randomly, but reinforcement learning there have been some fun studies that have shown that in a lot of cases, if you just took a bunch of random parameters, you can almost converge as fast and as well as some reinforcement learning methods on some problems. It depends on the structure of the problem.
Hmm.
Um, what that really means is what I'm really trying to say is that reinforcement learning is really slow. Like it's really slow and it's really costly. It will solve. I mean, it is a very powerful algorithm. It can technically solve pretty much any problem if you have infinite amounts of compute. So AlphaGo or AlphaGo, I forget how much it cost, but it was like in the billions to be able to train that thing, right? So if you have a few $1 billion, yeah, you can get a really nice paper. But but we're really trying to be like, okay, if you don't have very much data and you don't have very much compute, then what can you do, right?
Hmm.
And it turns out that using gradient-based methods, this is why most people try to make use of them. Because gradient-based methods just gradient-based optimization is just more efficient than non-derivative based. And now, there are some connections that you can put in there, right? So there are model-based reinforcement learning methods, which then use gradients of the model. And, that's where you're really starting to get into the space of saying, well, if I have a differentiable simulator, and then I put this I mix this differential simulator with a model-based reinforcement learning algorithm that is using the derivative. Now you're really getting into that scientific machine learning space where where it's a lot like these physics informed neural networks types of technologies, except it's using it to solve slightly different or sometimes similar problems. And actually, some groups have shown. So I think Samuel. I'd have to kind of dig it up to be able to find the reference.
Hmm.
I mean, some people have shown that using these types of adjoint techniques developed in this for the SciML ecosystem really improve the performance of reinforcement learning techniques on cases where you have physical simulations in there. Actually, one that comes to mind is Paul Shen wrote a very nice blog post on this. I think it's called like Neural ODEs and Reinforcement Learning, where he shows that with cart pull, for example, that's the classic. Can you keep the pull? Can you keep it balanced? Right? It's a physical simulation, and so if you actually write down it as here's a differentiable physical simulation, let's use the scientific machine learning techniques with the gradients through simulators and all that to train it. I think that if I remember correctly, it trains a neural network to control that problem in 4 iterations instead of the standard number. I think it was like in the thousands or tens of thousands with
Wow.
reinforcement learning. And so that really shows you what the performance difference really is, right? If you scale that, cart pull is something where you can do 10,000 iterations, and so you usually don't care. But when you
Hmm.
start saying like, oh, I want to learn the neural networks for what the missing force term, what the missing friction term on this aircraft simulation is, running that aircraft simulation can take you a day, and so you're like, okay, I need to, I can't run this 10,000 times. So that's where we're really the difference is. But there is a lot that we can learn and pull from with reinforcement learning. I've actually been getting some students who are doing reinforcement learning for this process. Kind of for me to kind of learn, for me to teach them the scientific machine learning tools and apply it in things that are traditionally done with reinforcement learning to show the acceleration, but also because I want to learn a bit more about some of the deep reinforcement learning techniques, to be able to see what details I can capture from there, to improve the scientific machine learning tools. So,
It's a
I mean, the
very
knowledge flow always goes both ways.
It's a super fascinating example with being able to train a cart pole agent so quickly by actually modeling the physical environment that it's simulating and being able to differentiate through it. That's definitely something that I will look into. And again, if there's any links that you have or references, I'll put them in the description as well for everybody to take a look at. Now, another question from Akash. This one we've, again, already covered a little bit, but we'll go over it quickly. Akash is asking, but how mainstream will Julia be in the commercial machine learning and AI industry? It isn't happening anytime soon, is it? Well, what I would say really quickly, just just to start off, is again, it's not really a competition with Julia versus anything else. And I think Julia already is pretty mainstream in the machine learning sort of, area, especially within scientific machine learning. What are your thoughts?
Well, I mean, I can tell you that there's more work for me to be able to do. There's more work for me to do than I can ever even do. So, like that's one way to put it. There's more emails coming in about collaborations and possible grant opportunities with someone, or so and so wanting to work with Julia Computing and wanting to pull me into these meetings. There's at least more work than I can ever want to do in my entire lifetime, and so that's at least good enough for me. So that means it's not this niche thing that that we're 10 groups are doing it. It's this niche thing where only thousands of people are doing it, and then they're all asking their questions to the people who really built the libraries and the people who are running these and the people who are consulting on it. So there's just so much going on, that maybe you wouldn't say it's mainstream, but there's still a lot more than you'd ever want. But yeah, it really is growing in a lot of aspects. One of the reasons is because of the scientific machine learning space. A lot of people are really getting interested in doing this in chemical simulations, pharmaceutical modeling, physical simulations, engineering and design of materials and batteries and these kinds of things, where standard machine learning methods don't really work that well. And so in that space, we've had a lot of people reaching out to us because of the scientific machine learning techniques, and that's actually why I've got this new director of modeling and simulation position with Julia Computing, because there's just so much energy growth in this space that I was like, okay, this is gone from academia to, I can no longer like kind of just send someone an email back and just say, yeah, tweak these few parameters and try this idea out from this paper, and you should be able to build a better battery. It turns out that there's so many of those requests coming in that I was like, okay, well, now we need a sales team, and now we need the pipeline, and now we need a whole so we built out this whole team just because of how many requests are coming in, for this type of work. So, I don't think that scientific machine learning will ever be the mainstream of machine learning, just because it requires such a distinct background. You need to know so much physics and all that it's not going to be your everyday machine learning engineer.
Mm-hmm.
But it is carving out itself to be a pretty large kind of world, right? This world that about with like Mathematica and MATLAB, right?
Mm-hmm.
Simulink, every engineer is using Simulink and CAD programs and Modelica. Really where that whole world is going, how people are designing bridges and aircrafts and all that. That's really moving towards this scientific machine learning space where you can say, well, let me design this bridge, but let me use some measurements about the area to be able to build a digital twin. So that way the bridge learns, friction properties that it didn't know about before. And now I change my bridge design using the data infused into my model. So this whole world of, which, I mean, that whole world itself is a hundreds of billions of dollar industry. If you look at Dassault Systems and MathWorks and things like that. So it's at least a pretty huge space to live in. So yeah. So I mean, bring it all back together. I'm not too worried if whether Julia is like fully mainstream or whatnot, just because there's just, even if you only look at is Julia going to be big enough in scientific machine learning? The answer is already yes. You could build a whole company around that if you wanted. You can
Hmm.
build multiple. There will be multiple companies around that. So
Hmm. There's a lot of work within using the world of Julia, and specifically what it's targeted for and the specific niche that it's targeted for. I feel like, I mean, as you mentioned, there's such a distinct background that you need for entering this kind of technology that maybe it's never going to be, this field in and of itself might not be entirely mainstream, but there is, regardless of that, a lot of work being done. Just because comparatively another field has a lot more work being done doesn't
mm.
mean this one doesn't have a lot of work. Um, so that's
Yeah,
definitely
I
really
mean,
interesting to hear.
yeah, everyone's like, oh, the hot thing today is natural language processing and image processing because everyone has images and everyone has images, everyone has language, so this thing is going to be, they're going to be big, right? But there's still a lot of very impactful things that do not fall into that space. Like, how do you design aircraft, right?
Hmm.
Or how do you design rockets, or how do you plan your missions, right? So what we some of the people who work with us in Julia are like the NASA Launch Services group,
Hmm.
um, and the people, Pfizer and Moderna, and these groups are doing a lot of these scientific simulations, which are not they're you can name off the big pharma companies just because there's so few of them, because there's only so many people actually like putting these chemicals together and such, but that doesn't mean it's not impactful, right? So
Hmm.
I kind of think that a lot of students should really be thinking about that as well. Just because I know that there is a young audience here. Like machine learning is going to have the bigger conference, but
Hmm.
what you really should be looking for is where can I make a major impact? And
Hmm.
what's going on in this next 5 to 10 years is there's really going to be a change in how every battery, every building, every bridge is designed, and maybe not as many people are going to be doing it, but that means every person who is doing it is going to have a pretty big impact.
Absolutely, right. It's even though it might not be as immediately attractive, where it's like, oh wow, look, this smart, personal assistant can answer my questions and tell me what the weather's like tomorrow when I ask it, right? It might not be as immediately attractive, but it is just as, if not in some cases, much more impactful than regular old machine learning AI technology can be.
Oh
It's
yeah,
the work that
I
we're doing in
mean,
the back end.
yeah, I mean, one interesting thing along the lines of that is, if Vox actually did a really nice video just not too long ago, about 2 months ago or something, on a new bridge design that was developed in World War II, where where General Eisenhower attributes that bridge design for winning the war because he was able to be deployed with a team only on one side. He didn't have to be on both sides, right? And so those are the kinds of things where just designing everyday objects to be better is pretty huge, and most people will never know the name of that bridge design. I forget it. I like this topic and I forget the name of that bridge design, but that doesn't, but it still had a really huge impact. I mean, just one of the things we're working on is improve battery life, right? So this is one of these cases where we're taking these microkinetic models and P2D models of batteries, and we're augmenting them with neural networks because just machine learning on its own isn't able to beat, machine learning on its own is not able to beat the state of the art battery models
Hmm.
because we know a lot about the physics and the chemistry of them. But a full model, with neural networks kind of stuck in there to be able to capture some of the chemistry that we haven't found out yet, is actually able to give 19% better degradation predictions, which means it's helping us find better materials for batteries, by having this connection there. And it's like, oh, 19%, that's not very much, but 19%, what that really means is if you really hit that full 19%, then you'll be able to hit the level of, hey, now it's more efficient enough to be able to fly now it's sufficient enough such that we can put batteries in an aircraft and use battery powered aircraft instead of instead of jet fuel. And so a lot of technologies are really at that edge where it's just like, if it was just 10% more efficient, if it was just 20% more efficient, now it's all batteries, now it's all, or like, and there's just so many disciplines like that if there's just one of those topics that you love, just go towards it and start trying to learn exactly how it's done. And there's just, I mean, there's just so much work in so many areas. So
There's so much more innovation to be done. Absolutely. There is another question here that I do want to get to from Noctis Kalis on YouTube asking epidemiological models combined with neural networks. I tried your published models, but if I change the model, SIR variations, ODEs become stiff. What is your experience with such kind of models?
Yeah, actually, we just put a preprint up. I think it might have been like a week ago or 2 weeks ago on stiff neural ODEs, which showed that there are a lot of issues with that come up in the training process when stiffness is involved. You have to completely change which adjoint methods you're using and such because even though a system, all physical systems are reversible, right? Like if you run physics forward, you run it backwards, you should get back to the same spot. It turns out, though, that numerical reversibility is extremely hard to do if you have this property called stiffness, which is if you have multi-scale systems. Like a way to think about this is, let's say we have actually, maybe I can show a picture.
For sure.
Um, if I could show a picture, I think that I can kind of illustrate this idea really nicely. So yeah, let me share my screen here. So yeah, so when I'm talking about what a stiff system is, right? Just because it came up in the top in the questions here, a stiff system is where you have two different time scales. Normally, what you want to have is you want to have your fast time scale be mean reverting, because if it's going to just keep on growing, then if it grows and it's growing fast, then you're going to hit infinity, right? So it's usually going to be something that's kind of mean reverting in some sense. And so here we have a slow time scale system, and we have something going really fast, right? Um, and the reason why these equations are perverse, or these models are perverse, is because if you're to ask the question of what is your derivative right here, you get an insane answer, right? It says your derivative is extremely large, and so let's do like the very the Euler's method, or the trying to just use your current information to project forward, right? So let's say this is a car, right? And so this is how every teenager drives, right? Where you hit the gas pedal and you realize you're over the speed limit, and you brake and you gas pedal. You're in this cycle, right? You're generally speeding up, but you're not speeding up, just in a simple monotonic way. You're speeding up and slowing down, speeding up, slowing down, and so so if you ask a question here, like how fast are you going? You're like, well, right, or how what is your acceleration? You're like, well, my acceleration at this point is 300,000, because like I've hit the pedal all the way down, and you're like, okay, well, let's project forward where you'll be in like 10 minutes from now. It's like, okay, you will have gone 500 miles per hour, and so therefore you'll be way out over here, right? And so when you look at the stiff system, right, like what you really mean by your and the real mathematical reason why this has a difficulty is because derivatives is local information, right? It's just like, oh, what's the tangent right here? What you kind of want to say is you kind of want to smooth out your derivative, right? Because if you're going up and down and up and down and up and down and up and down, you want to average out these and kind of say, your derivative should follow the light gray line, not this wild thing, right?
Mm-hmm.
This is what's actually happening. This is only what's happening at a very specific point. And so what can happen is that if you have these machine learning frameworks, or if you have methods that are trying to project forward from a point using just what is my change right now, you can get some absurd answers.
Mm-hmm.
And so at least on these kinds of problems with timescale separations. And so that's exactly what would happen in some epidemiological models, where you try to say, well, let me shoot up what is the infection rate due to COVID-19? Let's shoot that up, so that way you have this very steep, so that way you have this very steep drop, or you have this very swift change. And when you do that, if you have a machine learning framework saying like, oh, you always we have an R, maybe let's say it learns that you have this R of 2, right, which just means like for every person they infect 2 people, right?
Mm-hmm.
If they're right here, they're going to go, well, wait, this data point says I have an R of 500,000, right? So let's change our model, and let's say it's 500,000 now, and it predicts that you jump up to here, and most likely what you get is your training actually fails because it predicts infinities. So it turns out that you have to kind of do some very different things. You have to change around your adjoint methods. I have a whole paper that explains how you can actually start to make some stiff systems work, which is more than just changing your ODE solver. You have to change the whole training process. But you can also change your architecture, right? Because one thing that you can do is you can say the architecture itself is what's causing this problem, right? The architecture of I'm going to make use of my local information and project forward, right? So recurrent neural networks or LSTMs are something that does that. So we got to throw away that whole architecture. Neural ODEs kind of do that, but you can kind of do a few tricks. That's what one of the papers are. But can we do even better, right? So recurrent neural networks are out, LSTMs are out because they're projecting forward. What can you do differently? It turns out that there's also another problem, that gradient descent itself is such a projection forward, right? Because you're using a gradient to be able to tell you what parameters you should walk to, because your loss function should be the same. And so gradient descent, right? The reason why you jump out of holes with gradient descent, you have to make your learning rate lower, is exactly this kind of phenomena where if you take too big of steps, you can jump out of what you're thinking you're doing because your gradient's just too large. So anything with gradient descent is also going to have this problem. So what we came up with was this idea where you can say, well, let me have a neural ODE. Let me have a framework where I just fix, like when you have you only need, like an input layer and an output layer in order to have a neural network predict, arbitrarily many things, right? So let's just say we're going to just fix that input layer. We just, when you do the machine learning framework and it gives you some weights, you usually train those weights. Let's say the input layer's weights are fixed, right? We just leave them constant, and we only want to learn the output layer. Right. So if we do that in a neural ODE, so we have a neural network embedded within a neural ODE inside of an ordinary differential equation, where we say that the first part of the neural network is all fixed constants, and we only have to learn the last part of it. It turns out that if you do this exact procedure, you can do a trick, and you no longer have to learn via gradient descent. You can learn it as a least squares problem, which you can solve with SVD and all that, and you can get around all these issues with stiffness. And this is what we call the continuous time echo state network. It's kind of interesting because you have a second way that you can envision this whole system too. You can either think about it as a half neural ODE that is half constant, or you can think about it as I picked a random dynamical system. I just billiard balls with these are the masses, these are the initial velocities, and you just let the simulation run. Right, you just fix one of those, and you just ask, is there a way to be able to project from this arbitrary dynamical system to my original system? If you think about it, if you have a million billiard balls and you're trying to predict how three equations work, there should be some combination that gets close enough, right? And so the whole idea here is if you fix a dynamical system with a large enough reservoir, with large enough billiard balls, can you learn what your original system is? And turns out that that's quite true, right? So this gives us a way to be able to learn without requiring gradient descent, which then gets rid of this property. And I just want to show one figure that comes out of this talk, which is that if you want to learn these properties on systems that are highly stiff, here this yellowish line is LSTMs, and it's doing exactly what I said, right? It's looking at what the derivative is here now and saying, oh, the derivative is almost infinite, so let me go really large, and you can see it jump right back down, right? It does exactly what the method is told to do, and because that's what that's part of the mathematics of it, right? But the only thing that tends to work well on these kinds of problems that we found is this continuous time echo state network, because it is doing this fully implicit training. So maybe that's a little bit more detailed, maybe some tech details I'm throwing in here, but this tells you that one of the really interesting topics in scientific machine learning is stiffness, because pretty much everything in physical reality is going to be stiff. I mean, there are some counterexamples to that, like astrophysics. You just have things moving around. That's usually not stiff. But chemical reactions, modeling biological systems, you have the rate at which you digest. Digestion takes half a day or a third of a day, depending on who you are. But the chemical reactions within every single cell takes microseconds. And so you have this, so you have this thing where it's like, well, how much energy do your cells actually have? Each individual cell is moving on their own little kind of weird trajectory, and your body's metabolizing. And so you have this exact same, there's, talking about things with, 12 orders of magnitude of timescale differences is not hard to find in reality. And so this is one of these cases where standard machine learning fails, and we're finding we need special techniques for. This is actually segues into JuliaSim, but yeah.
Wow, that is really fascinating stuff. I mean, it's so great to see these kinds of specialized machine learning techniques and algorithms and toolkits specifically for these kinds of tasks. Like, how do you take something so chaotic but with a general sort of trend and train a system that's using fundamentally a derivative in order to be able to sort of fit to that data. That's really fascinating to hear, and hopefully that was able to answer your question, Noctis. Do let us know if you have any sort of follow-ups to that, and we'll be sure to cover
Yeah, I guess
that.
the one line TLDR is that yes, it probably, if you just took the example and made it really stiff, it would fail because you need to use new methods that just came. So yeah.
Use a new method. Wonderful. And we will link to these resources that you're talking about once again in the description, because I think that would be really interesting for people to take a look at. And you also mentioned that this does tie into JuliaSim, which I know is a relatively new piece of software. Would you maybe like to tell us a little bit more about JuliaSim, what it does, before we end the show today?
Yeah, so I mentioned that one of the, so you can use this to be able to learn physics you didn't know about, improve your model accuracy, right? But another thing that you can do with these that I mentioned quite early on that I didn't emphasize is that you can use, machine learning techniques to accelerate modeling itself, right? So we have some examples where, so let's think about, designing a building, right? You want to design it so that way it's energy efficient. So you have the building, you're like, where are my walls and everything? It turns out that like 90% of your model is the HVAC system, the air conditioning, right? Because how air conditioning works is really complex, right? Because you have this, you have this, it's your, you have your ideal gas media, right? So you always have like a halogen, or you always have like a helium. Yeah, it's an ideal gas. Sorry, I'm not a chemist, but yeah. So you have your helium in a little box, right? And you have to compress it, and so there's this whole dynamics about how the actual cold air is created, and then how that cold air is dispersed. And then, when it's in the building, it just kind of moves a little bit through the building, and how it moves through the building is going to be different based on the building designs. But it just turns out that the hardest part is actually just that one little piece, the air conditioning. So think about trying to create something like one of these buildings at like MIT or something, right? They have these really complex HVAC systems where they have 10 of the same air conditioner that is then flowing to different parts of the building, and you want to ask, how should I change the building so that way that is more energy efficient? um, it turns out that there is a lot of error in what we actually know about the system. I mean, we're not modeling the glass perfectly to know all the air that goes in and out, or so there are things that we're missing. So we don't need to get the air conditioner 100% correct. Right? So what we can do then is we can say, well, let's train a machine learning system to learn to be just like the original air conditioning with 1 to 3% error. Um, and now we can take that machine learning thing that we've learned and stick it inside of a building model, right? And then we can ask questions of, okay, given these types of air conditioning models, what does this tell us about the building we're making? If we chop off at a weird slant on the roof, does that change the amount of sunlight getting in? So that way we're saving 40% of energy, and also saving cost, And so you can analyze all these. These are things that architects have been analyzing with these design tools forever, with these software like Modelica and these SolidWorks and CAD stuff. Um, but when trying to do the full building, they couldn't before because most of the computation was just trying to make the air conditioning work. Which is kind of silly because we already know that we're not modeling it perfectly correct anyways, right? So where Julia similarly comes into play is it does exactly that, right? So let me kind of show a slide here again. So we basically show that, hey, if you want to do a full model of an air conditioning, so we took one that was from we were partnered with a Mitsubishi Electric, who does a lot of work actually in HVAC systems. Same as the car company, but it's their Mitsubishi Electric, their research division. Um, And so we took one of the models that they have of these heat cycles, which you can kind of just think about as an air conditioning, and we just asked, could we accelerate this with machine learning techniques that use these scientific machine learning principles, right? And this is actually where a lot of our scientific machine learning work started, because we started by saying, oh, let's try some LSTMs, RNNs, basic neural ODEs. It turns out that a lot of things failed on this because it has the stiffness property. You can actually see it because here's like a giant jump that happens, right? So we found this echo state, this continuous time echo state network works extremely well on this, where we can basically get to below 2 or 3% error in our predictions of how the air conditioning system will work. And what this means is, well, Julia is already a really fast system for modeling and simulation. So instead of the Daimola tool that they're using before, we're already 6 times faster. But then the machine learning framework brings it like 100 times faster than that. So we're talking about things that would have taken almost 2 years to run are now something that you can just say, yeah, that's one day of simulation.
Wow.
So so then you could be like, well, here's this whole building that we're like, we would have been like, getting the energy efficiency of this whole stadium would be impossible. Well, now it's going to be possible, right? And really, this is actually, I mentioned very early on, right? I was planting a few seeds, maybe accidentally, that composability is what really matters, right? So we're taking this idea of being able to surrogatize models with these Julia techniques of composability. So that way you can automatically take a surrogatized model and stick it within a non-surrogatized model. So you can say, here's my faster air conditioning, generate the code for building plus faster air conditioning and, replacing that. And this is how we can get to the realistic simulations where we are using machine learning embedded within it. And the nice thing about this is that, if you do it like this, if you've trained your air conditioning to be a faster version, you can try a whole bunch of building designs and you don't have to retrain it, right? Once you have a good machine learning model of air conditioning, you can use it anywhere. You can try it in so many different things. And so this composability mixed with the SciML tools is really kind of some of that secret sauce. This is the modeling toolkit framework that came out, all the symbolic computing stuff. But this also means that this opens up a huge business opportunity then, right? Because, well, if we pre-train something for you, then you get 100 times speed up and you don't have to do any work, right? So this is where we go, okay, well, let's create this whole cloud system where you can sign on to this cloud system, and we just have thousands of models available to you where you can say, well, give me the fast version of the air conditioning, give me the fast battery model, also give me some original models, so that way I can kind of compose them into the buildings, I can compose them into here. And now you have it's a super fast machine learning accelerated simulation platform where the users don't really need to be doing the training process, right? Because of how it's built. And this is what we call JuliaSim. This connection between modeling and simulation and these pre-built trained models and these surrogates and all of this kind of combined together. I think one thing that I left out of this kind of quick presentation of it is digital twinning, right? Which is that, so you can always do this thing where you say, well, I have an air conditioning and I want to change it from the real physical simulation to the neural network, right? But when you do that, you don't actually have to only use the real simulation, right? You can kind of mix it with data, right? So this is one of those things where I mentioned on battery problems, right? On generating more efficient batteries. We've already shown that you can create better models by using this type of surrogatization technique while inputting real data along with how we're training the surrogate, right? And so this is what we call a digital twin, right? It's something that is both learning to be a digital version that is based off the physical model, but also bringing in the data at the same time to actually be more predictive than our original physical models. And so what our platform is really doing is we're launching this platform where we say, here's some pre-accelerated models, but also all of the training methodologies are here on the cloud. And what we want to do in the near future with that is make it so that way you can just kind of upload some data and basically be like, well, here's the basic air conditioning model, but here's some real data I have in the system. Nudge it towards being what's like the air condition that I have, so that way you get a better prediction of the exact properties of my building. And this is really where JuliaSim is then both accelerating your models and also making them more realistic. Which it sounds like you can never do both of them, right? There's always a trade off between accuracy and efficiency, and or accuracy and efficiency. Yeah. But in this case, I just explained how we're solving that. So you can really get around that by mixing machine learning into this whole world of engineering.
Getting the best of both worlds, I see. That is super fascinating stuff. I mean, Julia Sim is way more interesting than I initially expected it to be, and being able to just drop in replace these sorts of actual handcrafted simulations with machine learning based sort of estimations of these simulations, I think is incredible. Again, it speaks exactly to the point of having the right tools as a developer from that sort of software perspective, having the right infrastructure, in this case Julia, being so composable and so flexible is what enables such amazing applications to exist, right? It's because we have those kinds of tools. And actually, really quickly, speaking of tools, we talked quite a bit about scientific machine learning tools and sort of how we're using them for SML, but I mean, there's a lot of cross-pollination within the world of technology, and I'm wondering how these kinds of tools that we're building for scientific machine learning might also go ahead and trickle down into the machine learning world as well, or vice versa, and sort of help everybody working on other kinds of AI applications leverage these kinds of tools.
Mhm. Yeah, so there is a paper that we'll be putting out pretty soon. Since it's going to be so soon, I can kind of give away the key idea here. And it's that as I mentioned, a stiff system is a very hard system to train, right? They're very hard systems, right? So one thing that you can do then is you can say, well, I want to learn a recurrent model, but if I let me take one step back a bit, right? So neural ODEs. They got popular in a lot of the machine learning spaces, not because of their connection to physical models, but because they are recurrent models but that do not require that you choose a given number of layers, right? You define a neural network in an ODE. The adaptive ODE solver says it takes 100 steps to solve this equation. That's a 100 step recurrent neural network, right? Um, and so what you can do then is you can say, well, let me kind of force it to do something interesting here, right? Let me force it to try to be the easiest differential equation to solve. If you do that, then you'll automatically be making it be a recurrent model that is learning to have the least layers possible, right? And there was a lab that did look at this, and they had this technique where you use higher order automatic differentiation. It took like an order of magnitude or two, more to train than the original one, but it did show that it is possible to make it so that way you learn, automatically what is the least number of layers to have for this predictive recurrent model, right? And so that's one. So if you can solve that problem faster, then you'd have something where you say you no longer really need to choose your how many layers in a recurrent model. This kind of a neural ODE with this kind of stuff in there will do it for you, right? And so that's where the literature was sitting for a bit. But we took a look at this and we said, well, how do you know when a model is going to be hard? Stiffness. And so, is there a way to be able to analyze the properties of the dynamical system to tell you if it's stiff? Well, there are. I mean, so a lot of the work I've done in the past is how can you automatically detect stiffness to be able to change which solver you're using on the fly, right? Well, I mean, so what you can do then is you can regularize your system and say, well, if I have a measurement for how stiff it is, I can regularize it so that way it learns to be the least stiff system possible. And if you tell it to do that, then what you're really telling it is, please, learn to be the recurrent, learn to be a recurrent neural network, that takes arbitrary number of steps, but make that be the easiest recurrent neural network, so that way you take the least steps. So then it becomes this way of automatically making your recurrent neural networks more efficient. And we've shown in cases like PhysioNet and some of these image processing cases where, yeah, it's able to learn a very small, efficient recurrent neural network that is, well, I mean, because an ODE is a continuous recurrent neural network, right? So it's able to learn a recurrent neural network that is able to do these things that is a lot more efficient than the original ones. It actually trains faster and everything as well, because it's just, as it's training, it's learning that, hey, I don't need all this extra information. Let's make it easier. Right? And so, so you can kind of get some like order of magnitude efficiency gains by using this kind of this connection, right? And this is really just a connection of saying, well, if you're doing machine learning with recurrent models, there's necessarily some dynamical system involved. And so if we want to make a machine learning method work better, well, that dynamical system corresponds to some kind of physical properties. We know some things about the physical properties. Let's control them so that way we have an easier system. And now you're back, right? So it's not quite scientific machine learning because we're not doing this to learn a physical system. But here you can see that this physical knowledge about learning is then trickling back to machine learning itself. So that paper will come out fairly soon here. So that'll be a fun one.
Very nice. I can't wait to read it. It should be really fun to see how we can make these machine learning systems more efficient. I feel like that's definitely a key thing to focus on. And as a matter of fact, something that I'm actually working on a couple YouTube videos on in collaboration with a couple different organizations. So make sure everybody stay tuned for that. And of course, Chris, I'll go ahead and put those links again in the description for your really fascinating work. Now, one more thing that I do want to ask you before we end up closing today's show is, I mean, we've gotten quite a few questions from the audience today, and we've discussed a lot about the world of Julia and scientific machine learning and machine learning in general as well. And through all of this, you've gotten a bit of a sense for what the audience wants to hear. And I wanted to ask if you have a closing message to share with everybody today to sort of leave them with.
Oh, a closing message. That's going to be hard. There's like 30 of them. I think that given some of the questions, it seems like a lot of people, a lot of people seem to be students. So I'll kind of keep to that vibe there. I think that one of the things I would tell a student, especially in the space of machine learning and programming languages, is really looking for something to do. I would say my advice would be to look for something that is going to be impactful, that even if it's something that's not popular, right? Because I mean, the reason why something gets popular is because it's been solved. So I always kind of find it funny how many people are still looking at natural language processing and image processing, right? Because it was great to look at that 10 years ago, right? Because 10 years ago, this problem of can you recognize a face in an image, and could you make something like Amazon Alexa work? Could that actually work well was like open, and no one knew if you could do it, right? And the reason why those topics are so popular today is because image processing works, and Amazon Alexa, Siri, Google, they're all a thing now, right? But that also means that you should also be looking at it and say, well, I mean, it got popular because it's working now, right? Like what's not working, right? Like that's the real thing you should be looking at. What's not working? Well, I just told you a few of these cases, right, where if you kind of stick an LSTM on a chemical reaction system, it blows up to infinity. But predicting how chemical reactions will work, that's my job at PUMAS-AI, right? This is how you make better drugs. This is how you predict how patients will react to vaccines, right? This is what's actually driving a lot of what's going on in the pharmacometric space, and that's a big area where people are looking at it and going, we don't know how to use machine learning, not because they don't know how to not because they don't know machine learning, but because when they tried it, it failed, right? And that's kind of like this interesting thing, right? Where when you see two things not coming together, you should assume that there's smart people around, right? Someone in pharma knows machine learning, has tried it. They're not publishing on it. They're not saying that it's working here because it must not be working. And so that's something that's very interesting, right? So I kind of say, look for things that aren't working. That's what's really interesting. That's what'll have a major impact. And where things are working, you can make natural language processing. You can probably make it a little bit better, so that way you don't have to yell at Siri so much. But there's all these other problems where it's just like right now you can't do a battery powered airplane, but if we do physics informed machine learning well enough, there will be battery powered airplanes. And it'll get popular after everyone sees the first battery powered airplane. But that means today is the right day to be working on it, right?
Absolutely.
So that's my one advice for everyone.
Wow, I absolutely love that, because that's something that is I feel like that's not the first thing that come to a lot of people's sort of minds. That is, Precisely as you said, the reason it's popular today is because it worked, right? Before the iPhone existed, before people actually, got used to using this new kind of, smartphone, whatever that was back then, it wasn't popular at all before that. Obviously, like internally, it was a huge like, what if will this work? And now that it does, of course, it's super popular and everybody's using it. And same thing with all this AI technology, NLP. Sure, there's some work to be done. Like, oh, can we generate natural language reliably? We've got things like OpenAI GPT that kind of mimic writing, but does it really write language, or is it just a reader that's really good at predicting the next word in a sentence or something? And there are lots of open questions like this, but at the same time, it's so much more of an established field than something like, as you mentioned, can we predict battery chemistry and how it works well enough to then be able to build a battery-powered airplane, right? So for all the students out there, look for those fields, look for those industries, look for those things to do that are still new, that are still fresh, where we have those unanswered questions. Work on answering those questions, and that's how we're really going to innovate and enable new things to exist instead of
Yeah,
just
and I
iterating.
mean, always follow what's going on in all these disciplines, right? Like know what's going on in natural language processing and all that. I mean, that's why I know about reinforcement learning, right? I'm following it because I'm like, oh, there are some nuggets that are coming out of here. But but I'm also just like, I'm not looking too much at natural language processing because there's this whole world of problems that could be solved, and each one that gets solved is a very major thing, right? You know. That's why PUMAS-AI has been working with Moderna, right? And a year ago, most people didn't think that getting a vaccine in under a year it would even be possible, and that kind of changed a whole lot of things in this last year, right? So it's these kinds of problems where it's like if it sounds like if it sounds like it's really cool and if it sounds like it's very impactful, just go for it. Like trust your gut instinct, because if you think it's cool, you can probably talk to someone in such a way that they will think it's cool.
Very
And
nice.
so there you go. Like, go have fun with it now.
Do what you're passionate about and what you think is cool, and where you think you can answer questions that so far haven't been answered, because that's where real innovation happens, when you like what you're doing and when what you're doing is new. Wonderful. Thank you very much, Chris. This has been super insightful. I've learned a lot from this episode, gotten tons of new ideas. We'll make sure to put all the links in the description below. And once again, also huge thank you to everybody joining in today. Of course, please do join us for next Sunday's Tech Life Skills 56th episode. Will be really fun. We'll get to hear from some technologists. Again, unfortunately, can't tell you exactly what it's about just yet, but make sure you join us next Sunday and you'll be able to hear more about it the middle of this week. Once again, thank you very much, Chris. This has been a super fun episode talking about the world of scientific machine learning and integrating machine learning into physical simulations, increasing efficiency by really, I mean, insane numbers, up to like over 500 times what we previously could have done. Quite literally bringing into the realm of possibility today what previously wasn't feasible to do is simply mind-boggling. As you mentioned, it can have impact on all kinds of things, from little things to really big things, like how quickly can we develop a vaccine for COVID, and so on and so forth. And so, yeah, once again, thank you very much. This has been a super fun episode, and thank you very much, everyone, for joining in today. Any other questions we couldn't answer, feel free to put them down in the comment section below, and we'll try to get back to you. But thank you very much, and goodbye, everybody.